So the problem I'm addressing here is current trial and error approach leads to missed opportunities and current method unsuitable for chaotic simulations. And what I want to show you is approach I started working on a few years ago. That is the shadowing approach for sensitivity analysis of chaotic simulations. So just one slide of giving you what the shadowing approach produces. So this is again a very short time chaotic simulation. When you increase this from 5 to 5,000, you get almost a parabolic. Now if you do shadowing sensitivity analysis to this t equal to 5 simulation, you get derivatives like that. Obviously, this is not a derivative of this noisy function, right? Because we expect this to be positive and negative all over the place. But it is an approximation to the infinitely long time averaged function. Okay, so that's what we try to achieve. And if you look at the slope, it is actually the slope of the parabolic, almost like a quadratic we get at the end. So how does this work? So let's again look at the Lorentz equation, the three-coupled ODE system. And here, what I'm looking at is how does the solution, which is the x, y, z, here I'm only looking at x and z, how does the solution depend on a small variation in the parameter, in the R? So different parameter is colored by different colors, so from red to blue. And as you see, as the system evolves in time, small differences in the parameter now becomes more and more different in the phase space. This is what chaos is. Chaos is, if you make a small perturbation, the difference just amplifies more and more and more as time goes on. And now you see that almost the same color can be in basically two ends of the whole space, whole phase space. So that means even if you make a tiny perturbation, the resulting realization or the resulting trajectory can be extremely different. And now I let it evolve further, I'm just skipping the video. Now you can see that there is almost no difference in the phase space that distinguishes one parameter to another parameter. Everything seems to be white, right? And this is the ensemble predicted by ergodic theory. So if you make small perturbations, almost doesn't matter if you look at the ensemble or look at the long time average or look at the distribution, which by ergodic theory is equivalent. Small perturbation makes not much difference to the ensemble. But here, there is actually a little bit of difference. You see areas in the plot that actually have some color other than white? Where?
The center.
Yeah, so you see a blue shade over here and red over here, blue over here. It's not a projector. It's actually the video. So these are the small sensitivities we actually are trying to obtain. The sensitivity of the ensemble or long time average with respect to a small change in the parameter. And you can see this is much, much smaller sensitivity than the transient sensitivity, than the sensitivity of the individual trajectories, how it responds to a difference in the parameter. So the real quest is how can we extract the small sensitivity of the long-time behavior of the ensemble to the parameter from this very, very large sensitivity of the transient without having to perform, in this case, 16 million simulations, right? For Lorentz attractor, we can perform 16 million simulations. For CFD, we can't. Okay, so the idea is the shadowing method. So it comes from looking at these snapshots of the video again, right? So this is an initial phase, this is a later phase. Now let me tell you what this is. This looks very similar to the left side, except for the color is all green. This is another ensemble of simulations, but with the same parameter. So here I vary the parameter slightly. Here I use the same parameter, but change the initial condition slightly. So this starts from the same initial condition. This starts from slightly different initial condition, but with the same parameter. So this is at the same time, and this is at the same later time. They look similar. Again, after even later time. So this is fixed initial condition, varying parameter. Fixed parameter, varying initial condition. Also look like the same. So changing a parameter looks like the same as changing the initial condition. That means, can we subtract a changing of initial condition from the changing of the parameter to distill, in some sense, the long-time behavior of changing a parameter? Right? We know changing the initial condition, if we trust the ergodic theory, has zero effect in the long-time behavior. But changing the parameter seems to have very similar changing effect, but at the end, it has a little bit of effect on the long-term behavior, on the ensemble. So if we can subtract this from this, maybe we can get the long-time behavior. And that's the idea of shadowing. So this is a combination of these two. So we are starting from different initial conditions and also with different parameters. And you can still see the spectrum. You can still see kind of the rainbow in this because they all have different parameters. But the difference between this and the last case is that this one we started with different initial conditions. A meticulously tuned set of initial conditions. Each parameter one initial condition that is specifically for that parameter. And also the rate of evolution for all of these points are slightly different. So that when we plot them, it stays together forever. The last one, by now it has already diverged, right? Now it stays for a long time. I'm going to play to the end, but it'll be doing this kind of things, stick together all the time. So yes, what we want seems to be the case that the shadowing solution, which is what we get here, solutions of the same differential equation with slightly different parameters, also starting from different initial conditions, tuned so that these solutions stick together for a long time. So if we can compute the shadowing solutions from a stable algorithm, and then we can actually prove on the very special cases that now if these U of T and S are a set of shadowing solutions, you can take the derivative to S into the limit. Right? This is a special case where you can exchange the limit and derivative and compute the derivative of the long-time average using these shadowing solutions. They are still stick to each other. They haven't diverged yet.